Thank you, and thank you to the organizers for inviting me here. So I gave the title of my talk to the organizers, and then I realized I had given not exactly the same talk, but a talk with a very similar title in Carry-le-Rouet 3 years ago. But probably I had forgotten about it, so you have forgotten about it also. So I'll start again from the beginning. And also there's been some progress on the subject. So this is a joint work with Alexander Kuznetsov, who's here, sitting at the back. So let me start with the definition of these varieties and how they fit in the classification of Fano varieties. So I will work over the complex numbers. So X will be a smooth complex Fano variety of dimension n, and I will always assume that its Picard number is 1. So, and I will choose an ample generator for the Picard group H, and so we write the canonical class as, so it's linearly equivalent to minus R H, where R is positive, because minus, because minus kx is ample, and okay, and there's also another numerical invariant, which is the self-intersection of H, and that's called, so R is called the index, and D is called the degree. Okay, so these are the two basic invariants. So there's a bound on the degree, which was proved by Kobayashi Oshiai. That the degree is at most n plus 1. And if there is equality, then X is isomorphic to Pn. So Pn, when R is n, X is a quadric. When R is equal to n minus 1, these varieties are called Del Pezzo varieties, and they were classified by Fujita and Ishkovsky. So this is Kobayashi Oshiai, and this is 1973. And so there's a classification here, which I won't go into. Ishkovsky, it's always difficult. There's number of K's and H's. Okay. And the next case, when the co-index is 3, they were classified by Mukai. Classification depended on a result which was proved later by Mella in 97. Okay, and one of the results, I mean, Mukai gives a very precise description of all these varieties, and in particular, he proves that the degree is an even number. That's easy. Any even number between 2 and 18 and 22. Okay, and so Mukai used the what is called now the vector bundle method, which was initiated by Gushel in '82, and this is why we call some of these varieties Gushel-Mukai varieties. So the case Gushel-Mukai is the case when D is equal to 10. So GM for short. So maybe I should have mentioned here if you're not familiar with this, there's a typical example when X is a hypersurface of degree D. Then it is Fano of index n plus 2 minus D and degree D. Okay, so this is an infinite family of examples. In the case of Gushel-Mukai, there's a very limited list. So let me state the Mukai theorem. So he wrote a series of articles. I don't know, I don't have a date. I just have a sort of a between 89 and 92, there was a...
Sorry, Olivier?
Yes.
All the plunging to Gushel-Mukai, but so what about the other degrees that you listed there? There's a classification?
Yeah. I mean, so you'll see what the classification looks like, and so there's this article by Mukai who says that, so starting in degree, maybe let's say 10 to be safe, they're all sort of a linear section of a sort of strange, I mean, Mukai-like construction. So very interesting, of course. So any a smooth complex Fano variety, Fano n-fold, say, X of index of, let's say, Picard number 1, and index n minus 2, so this is the n degree 10. So has dimension. So there are not many cases. They only occur in dimensions 3, 4, 5, 6. And they can be described as follows. Okay, so let me start. Okay, so I'm. Okay, let me start with dimension 5. There's the easiest. When n is equal to 5, the x, so x is my variety here, is the intersection of the Grassmannian of lines, I mean of projective lines in a 4-dimensional projective space, which are right at GR2 V5. So usually a V will stand. Sorry? Wait, it's not over yet. So when I write V, it's almost always a vector space, and the index is the dimension. So V5 is a 5-dimensional vector space, intersected with a quadric. Okay, so this takes place in the Plücker embedding. Okay. I was told by Americans that this was a G, not a 9. So, and then there's another case which I won't describe, which is called the, let's say, the Gushel case, but I won't talk about them. It's a degeneration of this first case. So when n is equal to 6, X is a double cover. Let's say maybe 6 here to recall what the dimension is. It's a double cover of this Grassmannian, branched along something of this type here. So let me write it like this. Okay. So this is what the Gushel varieties look like. They're double covers of something. Okay, when n is equal to 4, x4 is the intersection of x5 with a hyperplane, or the Gushel degeneration. And when n is equal to 3, x3 is the intersection with a codimension 2 linear space. Okay. So this is what a Mushel classification looks like. You start with a certain thing, and if you take a hyperplane section, the co-index remains the same. Okay, so you get a whole family of them. No, the Gushel case is exactly like this. So it's the double cover of. Okay, and then of course you could keep going, but then the next case will be a general K3 surface of degree 10, and the next case will be a general curve of genus 6. Okay, so these are the Gushel-Mukai varieties that I want to talk about today. Okay, so let me see. So why are they interesting? So as you'll see, they have interesting period maps, and they also have interesting rationality properties. So in these dimensions here, they're all rational, so not so interesting in that case. In this case, most of them, and probably all smooth ones, are irrational. That can be decided by looking at their intermediate Jacobian. And this case is very similar to the case of the cubic fourfold. Okay, so there are some known rational examples, but one expects most of them to be irrational. Okay, and then Sasha told me to add that they also have interesting derived categories. So I trust him on this. Okay, maybe I'll move on the small blackboard here. So let me talk about periods. So in all of these cases, there is always a map to the Grassmannian. So xn will be a Gushel-Mukai n-fold, and there is a map to the Grassmannian, which in all of these cases is an inclusion, but it also exists in that case here. So. Okay, so this we call the Gushel map. Okay, so if you want to look at the cohomology of this variety, the only interesting case is the middle cohomology, Hn, and there is sort of a constant part which comes from the Grassmannian. So we will define the vanishing cohomology as the orthogonal of what comes from the Grassmannian. So of course this is 0 when n is odd, but it's just for having a uniform notation inside this. So this is the vanishing cohomology. So, of course, it has a Hodge structure, and so one can compute the various dimensions of the pieces. So it's not completely obvious, but there is nothing really difficult. So the Hodge numbers are like this on the vanishing cohomology. When n is equal to 3, it's 0, 10, 10, 0. So that's on the H3, there are 4 pieces. When n is equal to 5, it's very similar. So 0, 0, 10, 10. 0, 0. And for even dimensions, it's 0, 1, 20, 1, 0, and here okay, so when the dimension is odd, it's a Hodge structure of weight 1, so you have a intermediate Jacobian, which is a principally polarized abelian variety of dimension 10. And when the dimension is even, it's a Hodge structure of a K3 type, so there is a period point, a period map to a space which is a quasi-projective variety. Okay, so there is a period in some space. I don't want to be too precise here, so period in some period domain D, which is quasi-projective. And it's actually the same, it's the same lattice in both cases here. So you have a period map to the same period domain. So let me talk about, so I'll move over here, this period map. So yes, for dimension 4 and 6, yeah. So let me, so I won't go into the details of constructing a moduli space, so let's assume that it exists, and let's call it curly xn. So what we have here are maps from, okay, so moduli space of Gushel-Mukai 3-fold and 5-folds to A10, the moduli space of principally polarized abelian varieties of dimension 10. And so the dimensions here, it's 22 and 25. And here, of course, it's very large, it's 55. Nevertheless, we'll see that these maps are not injective, although they should be in some sense. And then we have in even dimensions, x4, x6, so dimensions here is 24, here it's 25. And you see that x6 and x5 are very, I mean, they depend on the same number of parameters. And so we have a map which just goes into this period domain D, the same one. And this one has dimension 20. Okay, so these maps are not injective, obviously, and but they are dominant. Okay. So our purpose today is to describe these maps. Okay, and for that we unfortunately need EPW sextics. So I think that. As someone told me, someone I will not name told me once, if you hear the EPW sextics, you stop listening, except for Kieran, of course. So I used to be like that too, but not anymore. So let me just be very vague about the construction. I mean, this is an important construction because it's a geometric description of a general hyperkähler fourfold of degree 2. Okay, so there are not that many descriptions of general hyperkähler fourfold of any given degree, and this is one of them. So you start with a vector space of dimension 6, so V6 in my notation, and you look at the third wedge product of V6, and it has a natural how do you call it, skew symmetric form with values in wedge 6 of V6, so it's not well defined, but you can talk about Lagrangian subspaces. Okay, so the dimension here is 20, the dimension here is 10. Okay, and through a process that's not very difficult, but I don't want to give the definition, you can associate with this a sextic hypersurface in PV6. So let's say that this Lagrangian is general enough. There are some, I mean, Kieran wrote a lot about this, so there are some very explicit conditions that you need to impose on A. So let's say that it's good. This sextic will then be singular along a surface which are called Y2. So it's not a square, it's just index. I mean, it's not an exponent, it's just a notation. Surface, smooth surface. Okay, so these are called EPW for Eisenbud, Popescu, and Walter. Okay, thank you. But then Kieran showed how you can construct. I think you approached the problem from the other direction, trying to look for hyperkähler fourfold of degree 2, and he ended up with this description. You can construct a double cover. So this is the EPW sextic, and this is the double EPW sextic. Okay, and this is the one which is a hyperkähler fourfold. And it has a natural polarization, of course, coming from this map here, which has a Beauville-Bogomolov degree 2. And this is the general description of a hyperkähler fourfold of degree 2. So this one is smooth. So this is a double cover, I think. And I will call it F, I think. Okay. There's also there's this surface here, which is a surface of general type. Okay, you're not supposed to do that, by the way. Neither this. You have to be very gentle with the blackboards. It's a very dry climate here, so they all... Oh. Okay, so what's the relation with Gushel-Mukai varieties? Well, this was worked out by EDF and Manivel, and I won't go into the details again. So EDF and Manivel showed how starting from Gushel-Mukai variety. Sorry, so I forgot here, I mean, so let me add just one line here. There's also a double cover of this surface. So it's a double étal cover. So these are surfaces of general type. Okay, so this is all that you'll need to know about these varieties. Okay, so they showed, starting from a Gushel-Mukai variety, you can associate a Lagrangian A and an EPW sextic, I mean, as in here. It's a canonical double étal cover. Okay, so there's a canonical non-trivial two-torsion element here, which comes from the canonical class. The canonical class here is 3H plus this two-torsion point. So this is the.
Polymetric 2 was done by by, what's his name? That's the guy in Spain.
Velters.
Yes.
This double cover?
Yeah, because if you look at the surface could be the surface of tangent lines to the quadric surface in P3.
Yes, you're right, yeah. You're exactly right, yes, yes. Thank you. Okay, so, sorry for, okay, so now we're back to Gushel-Mukai varieties. So you have all this data associated with the Gushel-Mukai n-fold.
For all dimensions.
For all dimensions. Okay, so your EPW sextic is in some 5-dimensional vector space, and this so remember X is constructed from some V5. There's a V5 in the definition, and this V5 naturally sits as a hyperplane in here. So the first theorem is that there is actually, so the period of X is completely determined. So the Hodge structure of X is completely determined by the Hodge structure of A. So let me state it here as a theorem. So I don't know. So I guess I want to mention the name Logachev at some point. So at least in dimension 3, and then this is what we did with Sasha. So of course there are two cases whether the dimension is odd or the dimension is even. So first, when the dimension is odd, so remember in that case there is a 10-dimensional intermediate Jacobian, and it turns out that this 10-dimensional intermediate Jacobian, J of X, is isomorphic to the Albanese of that surface over there. Okay. And in the case of where the dimension is even, it's very similar, I'll come back to that later, to what happens with the cubic fourfold. And so here you have a isomorphism between, so this vanishing cohomology that I introduced earlier, equipped with the intersection product. This is an isomorphism of Hodge structure, polarized Hodge structures, and so on the other side, there is the H2 of the hyperkähler fourfold, equipped with the Beauville-Bogomolov form, and there is a sign which is -1. Okay, so if you don't know what this is, you don't need to know. I mean, you should know, but it's not necessary for this talk. So this is the. It's a quadratic form which is more or less canonically defined on the H2 of any hyperkähler variety. Yes, on the right there is a primitive cohomology. Yeah. So it's defined similarly. It's the orthogonal. So there's this Gushel map. I don't know if it's still there. Yeah, it's over there. So no, it's not the Gushel map in this case. There is a map from y tilde to PV6. So you take the orthogonal of the H2 of P6. Yeah, so I will explain that, yeah. I mean, I will explain where these isomorphisms come from. So what does this mean? Well, it's more precise than that, but it means that, so you see this thing here, which I haven't explained, translates into the existence of maps from X, curly Xn, which are these modalized spaces over there, to, let's say, and again, I will remain vague here, to a modalized space of double EPW sextic. Okay, so let me write it as E. So this was constructed by O'Grady.
How many models have the sextic, EPW sextic?
Sorry?
How many models do they have? What is the dimension of the family?
20. So it's constructed as a GIT modalized space. And it's a quasi-projective 20-dimensional. So a corollary is that the period map X for GM n folds factors as okay, so here it goes either to A10 or to D. Let me call that Q and call that P. Okay. So if you look at the dimensions, so here I mentioned that E is dimension 20. So this explains why none of these maps are injective. So more precisely, so when n is even, so in other words, 4 or 6, according to this statement here, so the period map goes into D, and this map P here is just the period map for this hyperkähler fourfolds, Y tilde. So when n is even, P is known to be injective. So this is the Torelli theorem proved by Verbitsky for hyperkähler varieties. In that case, for polarized hyperkähler varieties, so it is really injective. When n is odd, Q is not injective because it is known to factor there's a further factorization. So tau here is a natural involution on E, which is a duality involution on E, which can be described in several ways. The easiest is just is to say that if you have an EPW sextic, that's at least a general one, you can look at its projective dual, so the dual variety in the dual vector space. And it turns out that this is, again, an EPW sextic. So this defines a non-trivial involution on E, which was studied by O'Grady, again.
Can you say what Q is?
The Q is here. So you start from the EPW sextic.
How do you get the embedding right?
You start from an EPW sextic. You look at its singular locus. It has a canonical double cover, and you take the Albanese of this surface. So it's a bit complicated.
Is there a way to describe it in pure Hodge theory?
I don't know.
I think there must be a way by, yeah, if you blow up the EPW sextic, I mean, there must be some way.
Yeah, probably, yeah.
No, because I'm thinking in terms of the exceptional divisor that you get.
Are these maps dominant? Xn to E.
Oh, yes. Okay. So these are dominant.
It's like starting with a double P2 branch along the sextic and asking the H1 of the sextic. It's the same.
So
how do you get the principal polarization and the Albanese?
there's just via this isomorphism here. A priori, I don't know if there's a way to get it. Yeah, so actually the fibers of this map are, we know exactly what they are, okay? So maybe let me go. Okay, so I just wanted to, yeah, so if you have a Lagrangian A in wedge 3 of V6, you can take its orthogonal. And that's another way. It's easier to define it this way. So there's a conjecture, I guess, by Iliev, that the map here is this map here, Q prime, is injective. So actually, Atanas has a whole plan of for the description of the singular locus of the theta divisor. Of this principally polarized abelian variety. And so he has a plan of proof, which he made maybe some 20 years ago, but it's very difficult. It's actually, he wants to copy Claire's proof of the description of the singular locus of the intermediate Jacobian of a quartic double solid. I don't remember. Do you remember, Sasha? Does the intermediate Jacobian, 10-dimensional also, intermediate Jacobian of quartic double solid appears as a degeneration of these guys?
Of the same thing as before.
Yeah.
Because of the space of tangent lines to a quartic surface is a limit of
Yes.
the Y2.
Mm-hmm.
So I think it must.
Anyway, so he has this dream that this should be more or less isomorphic to, so it should be 4-dimensional and isomorphic to maybe a product, maybe not a product, but something like this. Okay? So in some sense, from the data of the intermediate Jacobian, you should be able to recover these two surfaces and then recover the thing. But I don't know if this is feasible or even if it's worth the effort, I don't know. Okay. Yeah, so maybe I will describe the fibers of this map here. It doesn't have a name, maybe E for EPW sextic. So the fibers of, let's say, fiber inverse of an EPW sextic. So of course it depends on the dimension n. I just erased the dimensions, that's too bad. And so it is actually, so remember I mentioned at some point, maybe it is gone now, that there's this, so the EPW sextic sits into this 5-dimensional projective space. But if you start from an Gushel-Mukai n-fold, you also have this hyperplane, okay? And so the fiber here has to do with the hyperplane here. So more precisely, I should say that the Gushel-Mukai n-fold is uniquely determined by this EPW sextic and the hyperplane here, okay? And I don't think this, so when n is equal to 6, it corresponds to choosing the hyperplane outside of the dual, so this should be considered as a point in a dual space. And in that dual space, there's this dual EPW sextic. Okay? And so what happens is that, so you're given your EPW sextic, and then you choose a hyperplane, so a point in the dual vector space, and depending where it is with respect to the EPW sextic and its singular locus, it will give you a Gushel-Mukai variety of various dimensions. So here, when n is equal to 6, it corresponds to the case where this hyperplane is not in the dual EPW sextic. Okay, so that's a 5-dimensional fiber, which is an open subspace in the projective space. N is equal to 5. Corresponds to something like this. So it's again 5-dimensional. It's a little bit larger open space. Open.
Understand? I mean, how the hyperplane determines something for n equals 6.
For n equals 6, I mean, I haven't explained how you associate with x this EPW sextic y. But there's a sort of it's determined by this EPW sextic and the hyperplane.
I'm not supposed to have understood.
Exactly, yeah. Okay, and when n is equal to 4, this corresponds to this hyperplane in the dual. That's 4-dimensional. It's too bad there. And when n is equal to 3, corresponds to taking this in the surface. Okay, so sorry, it's a bit crowded here. Okay, so anyway, I mean, what's important here is that there's we know exactly what the fibers of this maps look like. So in the last part, I want to explain how one can prove theorems like this. So the method is very classical and was used, for example, by Beauville and Donagi in their proof of a similar statement for cubic fourfolds. So let me go back to 1985. So in 1985, there were not many hyperkähler fourfolds known. At some point, they were even suspected not to exist. And so in this article, Beauville and Donagi started from the cubic fourfold. So let me choose another letter. Maybe this is not necessary, but okay. So this is a cubic hypersurface, so cubic fourfold, smooth. So this plays the role of the Gushel-Mukai variety, and there's also a hyperkähler fourfold associated with it, which is the variety of lines. So it's a variety of lines. It's traditionally called F, because it's also the Fano variety of lines, but it's not a Fano variety, so it's a bit confusing. Variety of lines. And it's automatically smooth whenever W is smooth. Okay. So since f of W parameterizes lines on W, there is a incidence diagram here. So let me get the letters right. Okay, so this is the universal line, so or the incidence correspondence. And so this is a P1 bundle. Everybody's smooth here, and so you can consider the Abel-Jacobi map. Which goes from H4 of W to H2, H2 of F of W. Okay, so what Beauville and Donagi proved is that this induces an anti-isometry. It's the same as for Gushel-Mukai varieties. You need to change the sign of one of the. So here you have the intersection product, and here you have the Beauville-Bogomolov form. Okay, so either you take minus the Beauville-Bogomolov form, and it's an isometry, or you call it an anti-isometry between primitive Hodge structures. Okay, defined as before. Okay. So in some sense, you need to find a nice family of curves on your variety, and then you manage to do some calculations. So in that case, the calculations are made easier by the fact that this is a P1 bundle, so everything is under control. Okay. So so the perfect analog in our case is the four-dimensional case. So there are several ways to approach this question. I mean, it depends on the family of curves that you want to consider. Lines are always good because lines don't degenerate, okay? So let's start with lines. So let's say Gushel-Mukai fourfolds. Okay. So of course it's going to be a very sketchy proof because I haven't explained to you. So you have a GM fourfold, and somehow there's an EPW sextic here, which I haven't explained how this works, and then there's a double cover, which I haven't explained either, okay? But let me just give you an idea. So we want to look at the variety of lines, same as here, containing X. So remember that X is inside the Grassmannian. So a line, every line in the Grassmannian is described as follows. So you pick a vector subspace of dimension 1, another one of dimension 3, and you look at the space of vector subspace of V5 such that, which is in between. Okay, so all lines in the Grassmannian are described like this. So in particular, by sending this line, and V1 and V3 are uniquely determined, and by sending this line to V1, you get a map to P of V5 by sending this line here to V1. Okay, so what will happen is that remember that this P of V5 sits in here. And there's a relation between this scheme of line here and this whole geometric setup here, which I will explain briefly. Okay, so it goes like this. So you have y. Okay, so this is the EPW. And you can look at the intersection of this sextic fourfold with this hyperplane. So this is a threefold, and it's singular. It's singular because remember that this guy here has a two-dimensional singular locus.
Because the point is in the dual.
Well, every line can be described like this. So to every line there is a V1 and a V3 attached. So you send the line to V1. Okay, so now you have this double étale cover. It's not étale. It's ramified along the singular locus, but this is smooth. So you take the pre-image of this, so this was called F. Okay, so it's also 2 to 1. So what happens here is that this hyperplane here is not if this hyperplane were general, then this would be smooth by Bertini. Okay, but it's not general. It's precisely in the dual of the hypersurface. So there will be some singular point. Apart from the fact that this guy was singular for other reasons, there's also singular points. So this one is actually 2 singular points. Okay, and so what we proved is that this map here, which we call sigma, actually factors through all this. And this guy here is a small resolution. It's birational. It's a small resolution of these 2 singular points. So this guy is smooth, threefold. So for that, you need some generality assumption on the whole situation, but which are very explicit. Okay, so now that you have this, you see that you can, of course, do the same construction here. So you will get a map from H4 of X to H2 of F of X. So this is the Abel-Jacobi map as before. And then you have to relate somehow. Remember, our aim is to relate H4 of X with H2 of H tilde. But it goes through here. So what happens is that you have a map from H2 of Y tilde Z to H2 of F of X through this pullback here. Okay, so you can one can prove that this is injective. The first one is just an isomorphism by Lefschetz theorem, and this is why you analyze what happens. And so this is where the isomorphism comes from if you restrict to the vanishing part. Okay, and so now I'm glad I was slow enough to I don't have to do the other cases. So for sixfold, it's very similar. Instead of looking at lines, you look at planes. Okay, and there's a very similar situation. And in the odd-dimensional case, there are various possibilities. You can look at conics, you can look at rational quartics, but in any case, there's a very similar proof in the other cases. I'll stop here. Thank you.
I mean, this map E, so it's always surjective. It's not I mean, the map is not just dominant. It's surjective, or
yeah, it depends how you define E. Yeah, it is surjective. You can say it is surjective. Yeah, yeah.
And you,
it's surjective on two. No, not surjective. I mean, you need to avoid some bad Lagrangians. But it's very explicit what the image is.
But you already studied, some compactification of these period maps, or?
You should ask Karen. It's complicated because nothing here is compact, and so trying to compactify the period map for EPW sextic is hard work, n'est-ce pas?
Oui.
Yeah, I mean, one would like to copy everything that was done for cubic fourfolds, but everything is more difficult.